Hello everyone, welcome to section 3.5. What we're going to talk about is the fundamental theorem of algebra. Okay, so before I go on to talk about the fundamental theorem of algebra, I'm actually going to do a couple examples that will actually lead us to what the fundamental theorem of calculus says. But what I'd like to do is I would like to give you a factoring strategy. So recall what we've been trying to do is we've been trying to factor polynomials so that we can find the roots of the polynomials and then hopefully graph them. So what we should have been noticing in the last section is we use the rational roots theorem. We try to find possible candidates for roots of a polynomial, and then we use synthetic division to factor. Now, all that was a great method, and at times we absolutely have to use that method. The problem is that it can be very tedious. We can have a really long list. And so while using synthetic division, the rational roots are why it's a great and it's a beautiful strategy. When possible, we should try to avoid it. So what I'm going to do is I'm going to give you a factoring strategy, things you should always try before you do the rational roots theorem. Okay, so I'm going to write factoring strategy. Factoring strategy. Okay, so I don't necessarily think that any of these are in any particular order besides the first one. The first thing you should always check for is see if you can factor out the greatest common factor. Factor out the greatest common factor. Maybe there's an x you can factor out. Maybe there's a common factor of 3 that you can factor out. The second thing I'm going to look for is I'm going to see if my polynomial has 4 terms. If my polynomial has 4 terms, something to try before synthetic division and the rational roots theorem is factoring by grouping. So, factoring by grouping. So you should see if, this is when you have a situation where the polynomial has 4 terms. So it's not that every 4-term polynomial you can factor by grouping. That's not the case. But I would always try grouping first. Polynomial has 4 terms. Okay. Something else I'm going to check for, if I notice it, is if something's quadratic in form. Okay. So this would be an example. Let's say I have something like, I don't know, x to the 4th. Let's say it's x to the 4th minus 5x squared. How about plus 4? So if we have a polynomial, this is a 4th degree polynomial. Well, this is quadratic in form because what I can think of, I can rewrite the x to the 4th as x squared squared minus a 5x squared plus 4. This 4th degree polynomial is quadratic in form. Sometimes I like to make a substitution. If y is equal to x squared, we can make a substitution, replacing the x with y. So this will be y squared minus 5y plus 4. And now you can easily factor this. I think this will factor to x minus 1. Y. This will factor to y minus 1, y minus 1, and y minus 4. And plugging these back in, what do I get here? I get x squared minus 1 times x squared plus x squared minus 4. X squared minus 4. And now notice each of these are differences of squares. So this polynomial factors to x minus 1 times x plus 1 times x minus 2 times x plus 2. So check if something is quadratic in form. Okay, what else would I check for? I would say after this, if you are able to break a polynomial down and get it into a quadratic, you should maybe try using the quadratic formula if possible. So, quadratic formula. The quadratic formula might be a good thing to try next. And once all of these are done, once you've kind of checked whether you can use these first 4 options first, then you should go to synthetic division. how about I write rational roots theorem? Rational roots theorem. So that's what I'm going to do. Now this is what I'm always going to check first. Try these first before we go to synthetic division. So what I want to do here is I just want to go ahead and do a couple factoring problems for you and make some observations. Let's go ahead and make our first observation with what we have here with number 4. So we're going to make some observations about how polynomials factor. So let's do math research. Math research. Okay. Observations. Okay. Well, notice here, let's just write down our first example here. Okay, that was this. This was we had the x to the 4th. We had x to the 4th minus a 5x squared plus a 4. Okay. We just realized we could factor this by thinking of this polynomial's quadratic in form, and we saw that it factored to x minus 1, x plus 1, x minus 2, and x plus 2. Okay, with this example, let's note something. Let's note something about its roots. Its roots, it has a root of x equals 1, has a root at x equals negative 1, has a root at x equals 2, it has a root at x equals negative 2. Notice that this polynomial, it has 4 roots. It has 4 roots, but what's the degree of the polynomial? Notice this polynomial, 4 roots, this is a 4th degree polynomial. So you might already kind of maybe start to get the idea of what I'm trying to hint at. Notice that we have a 4th degree polynomial and we got 4 roots. Coincidence? I don't know. But this is now an observation maybe we should start making when we're factoring polynomials. The question we should think to ourselves, if we're doing math research, is it true? Is it true that if I have a 4th degree polynomial, I'll always have 4 roots? Maybe if I have a 3rd degree polynomial, will I always get 3 roots? If I have a 10th degree polynomial, would I have 10 roots? I don't know. Let's do some more. Let's do some more. Okay. Let's do something really simple. Let's say I have a polynomial p of x. Let's say the polynomial is, let's say 2x cubed plus 10x squared plus a 12x. Here we have a 3rd degree polynomial. Let's see if it has 3 roots. Well, what I'm going to do is I notice I have a common factor of 2x that I can factor out of this polynomial. I'll be left with x squared plus 5x plus 6. Okay, so I get a 2x. This polynomial will factor to, I believe, x plus 2 times x plus 3. So now we can see this polynomial has roots. Its roots, well, x equals 0 is a root, x equals negative 2 is a root, and x equals negative 3 is a root. Notice that we have 3 roots. We have 3 roots. And this is a 3rd degree polynomial. So here I use the factoring strategy of looking for the greatest common factor. I got to a quadratic. You could have used the quadratic equation to figure out that the roots of this quadratic were negative 2 and negative 3, but it was just easier to factor. Okay. Let's do another quick example. I'm going to do a couple more examples just to get you the idea of what I'm thinking when I see a problem. Okay. So as another example, let's say I have a polynomial, p of x. Let's say it's negative 3x cubed plus 3x squared plus 27x minus 27. Okay. So I have a 3rd degree polynomial. I'm hoping to expect 3 roots. Okay, what can I do here? I'm first going to notice that I can factor a 3 out of all of these. This is a common factor of 3, but I'm also going to choose to factor out the negative. I usually try to not let if the leading coefficient is a negative, I usually try and factor it out. Okay, so let's factor out a negative 3, and let's see what we're going to get. If I factor out a negative 3, I'll be left with what? x cubed minus x squared. I'll have a minus 9x and a plus a 9. Okay. Now I need to factor this polynomial. Now you could try to use the rational roots theorem, try to figure out what our possible candidates would be the factors of 9. So you'd want to check plus or minus 1, plus or minus 3, plus or minus 9. But I'm noticing that I have 4 terms, so I'm first going to see if factoring by grouping is going to work. So I'm first going to always start with plus the opposite. Okay, I'm going to put these here in parentheses. And in each set of these parentheses, I'm going to factor out the greatest common factor. So let's see what we're left with. A negative 3. Okay, I can factor out an x squared. So I'll have an x minus 1. I can factor out a negative 9. Let's go ahead and factor out a negative 9, and I'll be left with x minus 9. Since I factored out a negative, there's a negative right here. Oh, sorry, I factored out a negative 9, so this will be plus 1. So I have a common factor of x minus 1, so this will be negative 3. I'm going to factor out the x minus 1. If you want, I can keep these square parentheses here. Factoring out the x minus 1, I'd be left with an x squared minus 9. Now, these big square parentheses aren't doing anything for me now, so I'm just going to erase those. Okay, and this factors to negative 3. I'm going to get an x minus 1. This is going to be an x minus 3 times an x plus 3. So we've factored this polynomial without using synthetic division. Okay, we have its roots. Its roots are x equals 1, x equals 3, x equals negative 3. Okay, so notice 3 roots, and we have a third degree polynomial. Third degree poly. Okay. Okay, let's do another example. Let's do another example. Well, let's say I have a polynomial. Let's say it's how about it's x to the 4th plus 2x cubed minus 4x squared minus 2x plus 3. Okay, so notice when I look at this polynomial, well, there's no greatest common factor that I can factor out. There's no factor in common between these terms. Also, this polynomial doesn't have 4 terms; it has 5 terms. So factoring by grouping won't work. So this is a situation where the only strategy I could think to do here is the rational roots theorem. So we're going to find our possible roots that we want to check. So I'm going to look at the factors of 3. So plus or minus 1 and plus or minus 3. If this has a rational root, then they have to be plus or minus 1 or plus or minus 3. Okay, so let's do synthetic division. 1, 2, negative 4, negative 2, and 3. Okay, let's check 1. Okay, so we'll bring down the 1. 1 times 1 is 1. 2 plus 1 is 3. 1 times 3 is 3. 3 plus negative 4 is negative 1. 1 times negative 1 is negative 1. Negative 1 plus negative 1 is negative 3. And oh my goodness, 1 times negative 3 is negative 3. Add those together, we get out 0. Yes! So 1 is a root of this polynomial, so x minus 1 is a factor. But remember, we should check to see if it has multiplicity of 2. It could go in there more than once. So let's check if it goes in twice. Okay, so we'll bring down the 1. 1 times 1 is 1. 3 plus 1 is 4. 1 times 4 is 4. 4 plus negative 1 is 3. 1 times 3 is 3. Add those together, we get out 0. Yes! So in this case here, 1 went into this polynomial twice. So now I've broken down this polynomial into a product of 2 linear factors and a quadratic factor. So we have that this polynomial, p of x, well that's going to be x minus 1, but it went in there twice, x minus 1 squared times, we have an x squared plus 4x plus 3. So this will factor to x minus 1 squared. Okay, let's go ahead and factor this quadratic. I think that'll factor to what, an x plus 1 and an x plus 3. Notice here, let's think about its roots. The roots of this polynomial, well, we have x equals 1, we have x equals negative 1, and we have x equals negative 3. Oh no. Oh no. Wait, I have 3 roots. But I have a 4th degree polynomial. Oh, man, maybe our observation isn't true. We were hoping that if I had a 4th degree polynomial, I'd get 4 roots. But I only have 3. But wait a minute. Maybe I do have 4 roots, but maybe I should just count x minus 1 twice. Yes, this would work. So how about, in this case, this polynomial would factor to x minus 1 times x minus 1 times x plus 1 times x plus 3. So I have that this polynomial will at least factor. It'll factor into 4 linear factors. It does have 4 roots if I count multiplicity. So if I say x equals 1 has a multiplicity of 2, I will say that I have 4 roots. I have 4 roots and a fourth, a 4th degree polynomial. A 4th degree polynomial. So I have 4 roots. I'm going to say including, 4 roots including multiplicity. Including multiplicity. This is great. This is great. Okay, let's do one more example. So far we've discovered, at least with our examples, that every polynomial we've seen so far has 4 roots. They may not be unique, but a polynomial will have 4 roots, including multiplicity. Okay, let's do one more example. Okay. So let's say we have this polynomial. May P of x is equal to, how about x to the 4th minus 3x squared minus 4. This is a great example of a polynomial that's quadratic in form. If you wanted to, you could do synthetic division on this. You could check plus or minus 1, plus or minus 2, plus or minus 4. But I don't want to go through that long synthetic division if I can hopefully notice that this is quadratic in form. So this is going to be x squared minus 3x squared minus 4. So if we call y being x squared, you don't have to do the substitution if you don't want to. I just think it makes the problem, look nicer. Okay, so this will factor to what? X. I need factors of -4 that add to -3. So some combination of 1 and 4. Okay, this number is negative, so the bigger of them has to be negative. Okay, so let's go ahead and make our substitution. So this will factor to x plus 1 times x squared minus 4. Okay. Well, we have x squared plus 1. This is a difference of squares that factors to x minus 2 times x plus 2. So we could think to ourselves, what are the roots of this? Well, notice here, for this one, x squared plus 1. Notice here, whatever value I plug in, whatever real value I plug in, when I square it, it's going to be positive, and it'd be adding a positive number to it. You can also think that this is a quadratic, x squared. It's been shifted up 1 unit. This piece will never be 0. Okay? So the only roots I can see here is x equals 2 and x equals -2. These look like my roots. But this makes me so sad. What? This makes us so sad. This makes us so sad. We have fourth degree and only 2 roots. 2 roots. But this is okay. This is okay, though. Wait a minute. Wait a minute. But what if I think about not just real roots, but complex roots? So in that case, if I'm thinking about complex roots, when would x squared plus 1 equal 0? Well, that's when x squared would be equal to negative 1. So if I square root both sides, that'll be the plus or minus square root of negative 1. We've seen this before. This is I. So x could be plus or minus I. So wait a minute. I do have 4 roots. It looks like I have 2 real roots, but I also have 2 imaginary roots. 2 imaginary roots. So I do have 4 roots if I consider complex numbers. I do have 4 roots. I have 4 roots. I have 4 roots. And it's a degree 4. A degree 4 poly. This is a degree 4 poly, so don't cry no more. We don't have to cry. We don't have to cry. We don't have to cry. We don't have to cry because we've realized, at least in this example, that yes, if we do consider complex numbers, we have the situation where I have a 4th degree polynomial has 4 roots. Now, how is this going to factor? How would this factor? Well, if I have I as a root, so x minus I would be a factor. I have negative I would be a root, so x plus I would be a factor. 2 is a root, so x minus 2 would be a root. And negative 2 is a root, so x plus 2 would be a root. So this polynomial p of x right here, factors into 4 linear terms. I have 4 roots. It's a degree 4 polynomial, but some of them might be complex. And sometimes this will work, but sometimes we have to count the roots more than once if we take, for the case of multiplicity. So what we've just discovered here is what's called the fundamental theorem of algebra. I'm going to go and write that up. This observation here, that if I consider the possibility of complex numbers, then every polynomial, every nth degree polynomial will factor into n linear terms. So every polynomial of nth degree will have n roots, including multiplicity, but some of those roots can be complex. This is the fundamental theorem of algebra. The fundamental theorem of algebra. This is what it says. If I have a polynomial, p of x, which is a sub n x to the n, plus a sub n minus 1, times x to the n minus 1, plus plus a1x, plus a naught. The fundamental theorem of algebra. If I have a polynomial, any polynomial, like this, factors to, well, I'll have a polynomial p of x. There could be a number I could factor out front. Maybe I'll just call that c, maybe a common factor. Okay? Or I don't know how would I put a? So it'll factor to a times x minus, what's the notation I use? X minus c1, x minus c2, x minus c3, all the way to x minus cn. Any polynomial will factor into the product of n linear factors, which means this polynomial will have n roots. So an nth degree polynomial has n roots, counting multiplicity. Counting multiplicity. That means it's possibly that C1 and C3 possibly are the same. Okay? What should I say here is that that C1, C2, all of these C's, all the way to C sub n, these could be complex numbers. Are complex numbers. Remember, every real number is also a complex number. A real number, any complex number is in the form a plus bi. A real number just has its imaginary part as 0. So this is saying that I can factor an nth degree polynomial into n linear factors, which means it'll have n roots. It's the possibility that these could be complex numbers. They could also be real numbers, but a real number is a complex number. And if I count multiplicity, this is what the fundamental theorem of algebra says. In the next video, I'm going to do tons of examples of using the fundamental theorem of algebra, and any polynomial we're given, we need to be able to factor it into n linear factors. We'll see you then. Take care.